Okay, I think we can start. Welcome. Today we have a special guest, Carlo Barbante. The presentation is very, very interesting. Why the poles matter. It is really difficult to summarize Carlo Barbante's activities in just a few lines. I try to do my best. Professor Carlo Barbante is full professor at the University of Venice, founder and former director of the Institute of Polar Sciences of the National Research Council. He is mostly known for his works on paleoclimate reconstruction in polar regions. He has participated in several expeditions in polar regions and in the Alps, and is the principal investigator of the EU Horizon 2020 Beyond Epica. It's quite a famous project. Professor of Earth Climate at Foscari, Harvard Summer School, he has been granted by the European Research Council, the ERC, with a prestigious advanced grant. Professor Barbante has been professor at the Accademia Nazionale dei Lincei and is an elected member of the Accademia Nazionale delle Scienze detta dei XL and of the Istituto Veneto di Scienze, Lettere and Arti. So welcome, Carlo. It's your turn. Thanks.
Thank you very much, Fabio. I don't know if I have a mic here, maybe this one.
Per parlare usare quel microfono?
Si sente? Okay. Thank you very much, Fabio, for the kind introduction. It is a great pleasure and honor to be here celebrating with you the 25th anniversary of the ENGV. I also have the honor to be part of the scientific board of this fantastic institution that I'm starting to know little by little in the past few months and hopefully in the next few years. I'm devoted most of my life in working in polar sciences as a chemist. I'm an analytical chemist by education, and so I work on developing a lot of different methodologies for ice core analysis and helping interpreting the long records of the climate of our planet. And I'm here to speak about why poles matters and why we are so very much interested in the poles. In this strange figure, you see both the Arctic and Antarctica together, and of course there are similarities and differences, and important differences in between. The similarity is that they are both areas which are centered in the geographic pole. They have, of course, long, cold winter and short, pretty cool summer. They are, of course, the home of glaciers, the home of strange animals that lives in remote regions. They both have seals, birds, whales, krills in the ocean, and that makes a big difference. They are among the region where the precipitation is the lowest. And if you consider central Antarctica, you have a very few centimeters of snow falling down every year. So it's a very little. And difference is, of course, the main one is that the Arctic is an ocean surrounded by lands, and that's today is a big problem because nearly 50% of the Arctic is Russian Arctic, and so we have reduced dramatically the number of observation in this part of the area. And while of course Antarctica is a continent surrounded by the sea, the Arctic is covered by a very thin layer of ice. Not everywhere, as we will see, especially in the last few decades. While of course Antarctica is a very thick ice sheet that in the thickest part is more than 4 kilometers, and of course preserve an important record of the climate of the past. The Arctic is inhabited. We have about 4 million people living in the Arctic region, while very few stays in Antarctica, mostly based on the station and the permanent station. And also, as you know, Arctic has polar bear, and while Antarctica has the penguins, and no more than that. So there are many reasons why we are very much interested in this region, and I can summarize them in these main 5 things that we will discuss through through the presentation. Of course, the polar region are pillars of climate sciences. Whatever happens in the poles doesn't stay in the pole, but is spread around the lower latitudes, and even the current climate is magnified in polar region. Is a not spot of anthropogenic change for many reasons, melting of the ice, both continental and sea ice. From a biological point of view, the polar region is a niche of biodiversity. We are witness of a big change in the change of biodiversity, shift from north to south and vice versa in the northern hemisphere. Atlantification of the Arctic is all problems that we will briefly deal with. And some of the tipping points, the threshold which our climate system is experimenting today are located in polar regions. So a large part of those are located in polar region. And then I would say is a cradle of climate science, is a real laboratory where we can retrieve many different information. Most of what I'm going to say is coming from this important report from IPCC. This is one of the special reports on ocean and cryosphere in a changing climate, and more also from our research and review paper. Well, pillars of climate sciences, we know that the CO2 is increasing everywhere, and that's a common feature with greenhouse gases. We are above the 420 parts per million continuously since the more than 200 years ago. We have an increase in sea ice, and this reflected into a warming of our planet, which is not equally distributed. And if you look at the last 100 and something year, 140 years, the increase in the temperature on our planet has been not uniformly distributed. We have places in the world which warm faster, others that cool down very quickly. But basically, during the last 140 years, we have an average an increase in temperature of about 1.2 degrees. But if you look at the polar region, and especially the Arctic, we undergo to what is called an Arctic amplification, an anomaly of the Arctic. So where we have an increase in the temperature in the Arctic, which is nearly 4 degrees, an anomaly of 4 degrees, which is by far the largest one. And Antarctica, which was considered to be in a steady state until the end of last century, has demonstrated during the last 2 decades to have a anomaly, especially in the Weddell Sea and the Antarctic Peninsula, where the mass balance of the continental ice is start to be very negative. And also the sea ice, we'll see, is something which is degraded very quickly. As you know from paleo record, we are experiencing dramatic changes during the last few millions of years, and we went through the last starting from about 50 million years ago, a continuous decreasing trend in the temperature, of course with differences in orbital parameters and in climatic condition, which is clearly visible, especially during the last few million years. And this is, of course, stays together with the changes in atmospheric CO2, and there is a clear interlink in between the two. And especially, we can compare, looking at what happened in the past, that we can compare it with the current trends, either in temperature and in the CO2, and especially having projection into the future. So comparing different socioeconomic scenarios of CO2 emission with the increase of temperature. And well, if you look at this is a record of CO2 which has been taken by an ice core in Antarctica. We'll see in detail in a few minutes. Well, you see that basically during the last couple of million years, we never had greenhouse gas concentration as high as we have today. And again, I told you that one of the most important things is the increase in the phenomenon called Arctic amplification, which has been seen at the first time many years ago, already in the 70s and 80s by Sicuro Manabe, who won the Nobel Prize in Physics in 2021. And actually, if you bring the latitude here with the 90 degree north, especially in there, he already predicted a tropospheric warming with time. And this is something that came out also very recently, in which you have an increase in the temperature both in height and in the latitude gradient. If you see it here, the Manabe paper that has been published in the late 80s, in which he foreseen in the future years an increase in the temperature in the polar Arctic, in the Arctic, has been also proved very recently with a new modeling exercise that has been run recently by Thomas Stoker and the group of the University of Bern. So this is not something that is really happening from, and we can see from the data, but it's something that you can model and you can really literally take care looking at the polar and climate dynamics that we can look at. So, well, the polar facts is that CO2 concentration is increasing. It is increasing since, well, it's the highest, at least during the last 2 million years. And we mostly see that looking at ice cores. Ice core is a fantastic time machine. We have many archives that can store information about the climate of the past. Of course, you all work on marine sediments. We have very long sedimentary history, for instance, in the Ross Sea, covering hundreds of climatic cycles, stadial and interstadial. But the ice cores preserve inside both information from both forcing factors and response. So you can have greenhouse gas concentration, you can have the dust and chemistry inside the ice, and also the information about the temperature and precipitation. And especially these tiny bubbles, which are inside the ice matrix, contain the air of the past. And is that the reason why we are trying to look at that? We are trying to read into this time machine with digging deep ice cores in Antarctica. We can take them out using manual corer or even mechanical corer, reaching far back at the time of 800,000 years. And the deepest ice core drilled in Antarctica is still the one that taken in Russia, in the Russian station called Vostok in the late 90s. Well, we go there, as I told you, and we have a continuous sedimentation of layers, so of snow layers, and then those snow layers are then transformed into ice. One peculiarity is that usually the channels inside the ice, inside the snow, and then the ice is still open, so the air can diffuse inside and can, of course, record what happened in the past. But it is the air. It is usually younger. It is usually younger than the associated ices, because the close-off happen at a certain depth. But we are quite good enough in understanding the differences in between the age of the air into the bubble and the ice itself, because we know the diffusion law, we know the gravity, we know the mass of the molecule that are diffusing. And so we can assign good age, pretty precise age on that, and also on that, and also at the ice. And you'll see that the record of the CO2 concentration during the last 800,000 years, which follow the stadial, interstadial changes in climate linked to the orbital parameters, especially tilt and precession, and you can also see, and this partially the ice core record overlapped with the observation, atmospheric observation. You see the dramatic increase over the last few decades. So if the CO2 concentration always oscillated in between 180 part per million to 280 part per million in the last four interglacial. Now we are above 420 part per million. So we never had something like that, certainly in the last 800,000 years. And we can see directly from measurements on ice cores. But even if we go far back in time, looking at boron isotopes in marine sediments, or also looking at fossil ice in Antarctica, where we have discontinuous ice, we can look at the concentration, which are definitely within the range of natural variation, so between 180 and 280. So it tells the Antarctica tells that something is happening, and there is a lot of things we can understand from there. Then I tell you, is clearly an hotspot of the anthropogenic change. For instance, the sea level and the average sea level is increasing very quickly. Is the fastest rate, at least in the last 3,000 years. Of course, we have a complex situation linked to the sea level rise, because it's tightly linked to the rebound after the glaciation, to the soil rebound after the glaciation, but is also linked to the melting of the ice. I started to work in Antarctica 30 years ago. My first mission was in 93, 94. And there was at that time Silvia Pondrelli or Georgiana was there with me at the first expedition we had. And I never seen something like that. Water flowing above the ice sheet. And it's something that we start to see quite often in the last few seasons. So ice is melting, and is melting very, very quickly. And since the beginning of the 2000, the beginning of this century, we do have satellite altimetry and gravimetry, which measure for instance, the ice loss in Greenland or the ice loss in Antarctica. So you see that for Greenland we have a progressive decrease in the continental ice, which is very important, especially in the coast. So you have ice loss both from the top, because the ice is melting from the top, and is also melting from the bottom, especially where you have the ice shelf on the sea. The ice is melting because of warm, or let's say less cold seawater is degrading the ice from the bottom. The speed is alarming. We are going at the speed of 271 gigaton of sea ice, of continental ice per year. This corresponds to about 0.8 contribution of 0.8 millimeter of sea level rise per year. Is quite a lot, and especially this number that might be difficult to completely put in place, but I tell you is about 420 swimming pool every minute. So with the melting of ice of Greenland, we can feel about 420 swimming pool. Of course, Antarctica is, especially during the last few decades, going in the same direction, with the, I would say, in absolute terms, in the less contributing less. But then we also have glacier from the third poles, glacier from the Alps that are contributing dramatically. Just to give you an idea, in 2022, ice, the Alps, the mass balance of the Alps were, the glacier of the Alps lost about 6% of their mass in 1 year. And it was 3% in 2023 and 3% in 2024. So we are losing mass at a very high speed. And if you look at the sea level rise, you see this curve, which is already coming from satellite altimetry. You see, okay, an increasing trend during the last few decades, but the speed of the increases is very, very high. In the most recent years, in the last decades, from 2013 to 2022, the sea level rise was about nearly 5 millimeter per year. And if you start to multiply 5 millimeter per 10 or per 50 and so on and so forth, you'll see that it's dramatically alarming, especially for coastal cities. Again, Another important fact is the Arctic sea ice. Arctic sea ice is also melting very, very quickly, having a shrinkage of the area of the sea ice in the northern hemisphere, which is really important. We lost more than 50% of the ice coverage, and it's not just the surface, but it's also the thickness. You know, we don't have any more, or very limited amount of what we call multi-annual sea ice, so ice that pile up year after years and bring you to the very thick sea ice. And when I say very thick, it means that we are used to have close to the North Pole 3 or 4 meters sea ice thickness, and now we don't have it anymore. I tell you, you know, I look at a lot at that, so I quite familiar with the statistics of sea ice, and of course everybody of us, when we think about the Arctic, are always thinking about the epic exploration, you know, well, the boys of Barrow, the admiral of the British Navy and so on, and the Erebus and Terror in the Arctic that were trapped in the ice. But I tell you, I was in a ship last year on an icebreaker sailing to the North Pole, 90-degree north, where I told you usually we had conditions like that with a very thick sea ice. And these are the very last few minutes arriving at 90-degree north at the North Pole. You see open water everywhere. So I've been touched very much of this because as I told you, I know the numbers, I know the declining trend of the sea ice both in surface and thickness, but well, I would have never imagined that we can go through with an icebreaker on just 30 or 50 centimeters of ice. So this is the condition at the North Pole in end of summer. This was at the 31st of August last year. So this is the dramatic condition that sea ice is having. This is exactly 90-degree north, the North Pole, with open water everywhere. Of course, this opened many considerations to the navigation to the Arctic, to the opening new routes into that. But it's something really touching. I mean, I thought a lot about that. And Antarctica, the sea ice in Antarctica is also changing. We had it on a steady state for the decades in which we have satellite observation. So from the 80s to the 90s and then to the new millennia. And now since 2015 we have a trend possible. I mean, we still have to confirm in the coming years, where also sea ice around Antarctica is going down, is deteriorating. Well, that's another important step. Then the third point, while we are so interested in polar region, is that those regions are really a niche of biodiversity. There are a large number of polar species which are contracted and are literally disappearing. There are great variety of species. We rely a lot on the fisheries, on the organisms that lives into this area, and most of them are very, very peculiar. So they adapted to this cold region. Studying them, we understood a lot about biotechnological application, and of course the adaptation of these organisms is something really interesting. Well, changing of temperature of the ocean water, especially in the Arctic, causes a migration of species. We have seen many pictures of polar bears moving because they don't find food, and the same happened to the fishes, that they are moving. Some of them are moving north, where they can find colder water. And we see many fjords of Greenland and Svalbard archipelago, for instance, a lot of alien species and species that they didn't exist until a few years and decades ago. So we have a quite big knowledge gap in understanding the changes that are happening, and those regions, from many point of view, are undergoing to a very, very cold called change in the biodiversity and in the species. If you sum up also the shrinking of the sea ice, the warming of the water, the increased pollution, which happen directly in the Arctic, for instance, and also deriving from outside, that's changed a lot the biodiversity, and so it's something that we have really to worry, because all that reflects, for instance, in the changing in the capacity of having food also at the lower latitudes, and we are very much interested in that. So, well, again, I told you we are very close to some of the tipping point, and most of the tipping point are very closely related to polar region. We had them in the past. We also had them, some of them in the past. This is, for instance, a record of the last 130 years of climate reconstructed in Greenland ice core. We go from the right, 120,000 years ago, and today. This is the last glacial maximum. This is the Holocene, the current warm period. This is the Eemian, the previous interglacial. And as you see, during the last at least 80,000 years, we had these huge changes in temperature, which are called the Danskar-Oeschger events. We have about 25 of them happening during the last glacial maximum. These are very peculiar, those what we call abrupt climate change. So changes in the temperature that happen especially in the northern hemisphere with a very high speed, about 40, 50 years with an increase of about 10 degrees in temperature. So it's something that is happen very quickly. They usually come in cluster of three. They are tightly associated to changes in ocean and atmospheric circulation, and then very quickly, well, less fast than they came in, they are going back to the cold one. So these are very important periods. We know quite a lot about that, and especially we know that they never happen in interglacial periods. So we are therefore very much interested, because what we are doing now is to most likely to have an abrupt events in a warm period, or in a warm climate. So tipping point is very, very important. What's so called the threshold points. You have a forcing, for instance, like the greenhouse gas that increase very quickly, and is exactly what we are having now. And then we have a response. You know, the climate can respond in many, many different ways. For instance, the temperature can respond quickly and goes on a new equilibrium line, or respond slowly, or even readapt in a new equilibrium. And when you take out the forcing, the system can react, and can react in many different ways. It can drop down immediately, coming back to the equilibrium state that we had before, or even cannot react to the change, and so stays in a new equilibrium. And this is what is happening, and this is what we call a real tipping point. So something that will never go back to the previous status that it was before. And we have many into the planet, many into the climate system, and most of them are tightly linked to the polar region. For instance, the loss of ice in the Greenland ice sheet, the permafrost loss that is another big important issue. The shift of boreal forest from south to north, the loss of sea ice in the Antarctic Peninsula, and many, many others. Of course, you have other things like this happening, for instance, in a tropical region, but the most of them are tightly linked to what is happening in the polar region. Among those, I want to show you an example of what is happening as a clear tipping point in Twice Glacier in Antarctica, in West Antarctica. Well, again, you have different forcing and response factor on the different time scale. In this case, when you have large forcing, and you might have small response, and then the system go back to the previous state, as we have seen before. But you can, and then on different degrees, but then you can have even states in which the forcing goes at a certain extent, and the system is no longer able to go back to the previous stage. And this is what is happening, for instance, on Dwight glaciers on this region, where you have basically a huge loss of sea ice, and the sea ice is exerted like a barrier for the ice sheet and for the continental ice. And when you have a loss of sea ice, the speed of the continental ice increase, and you have therefore an enlarged velocity. So those are one of the most unknown component of the climate system. And when you look at the future projection of the sea level rise, also from the IPCC, you see that there are what they call low probability but high impact events, and are tightly linked to what is happening in polar region, because we don't know what completely what mechanisms are behind these events. And so it is exactly something like this, those low likelihood, high impact storylines that show you that, depending on the scenarios, and this actually is not relevant which future socio-economical pathway will follow the emission, because even with let's say with an intermediate scenarios with SSP 2 to 4.5, increasing the radiation, you might have a low likelihood high impact storyline. So something that can happen like this, and those high impact storyline are tightly linked to what is happening, especially in Antarctica. So we have and we have to know much better where really if we are entering in a system like this. And as you see, well, if at 200, 100, and at the end of the century, we can project in the worst scenario 1 meter of sea level rise. In this case, if we have a collapse of the Western Antarctic ice sheet, you might have much, much worse, which goes above 1.5 meters, or on a longer time scale, the projection show that you even might have scenarios of 2 or 3 meters increase in sea level rise. So that's the reason, another additional reason why we are very much interested in the stability of the ice sheets and in the future climate change of the polar region. And then last but not least, I want to tell you an important story, which is the fact that the polar region, and in this case Antarctica in particular, is one of the cradle of the climate science. Is a clear one of the best laboratories that we have to study the climate of the past, and is there that we are seeking the oldest ice. I told you, I've shown you that we have this fantastic iconic record of temperature and CO2 over the last 800,000 years. But well, if you look at that, the 800,000 year is exactly in the middle of an important change into the history of our climate, and this is the so-called the mid-Pleistocene transition. Is an important transition which is happening exactly, well, the ice core record stops here, and exactly in the middle of this mid-Pleistocene transition. And this is a very important period of time that happened 900,000 years ago, in which we have a transition from a periodicity or a fluctuation in climate system from about 41 kilo years, which is tightly linked to the obliquity of the orbit of the planet, to a larger, more ample fluctuation. That means a larger fluctuation from cold to warm during glacial and interglacial, and with a decreased frequency, so with a periodicity of about 100 kiloyear world. Well, it's not clear what's the reason why, because we have this mid-Pleistocene transition. There have been evoked many different causes. It is certainly not orbital, because I'll show you that the orbital parameters were still the same. But it's a very important period of time because the mode of the climate changed quite dramatically. So changing periodicity, it becomes more difficult to deglaciate. When you have huge ice mass, it's more and more difficult to deglaciate. And this is an important period, because we also had a bottleneck in a human evolution. This is a paper published by Chinese group, and also Giorgio Manzi was involved in Science last year. We go from 1 million years ago to today on the vertical axis, and this is the number of the hominid individuals spread around the world. So we had about 100,000 individuals before the mid-Pleistocene transition, and something happened exactly at that period of time. So there was a bottleneck in evolution, and they could reconstruct thanks to genomic modeling, the number of individuals that were living in a certain period of time, and it dropped down to about 1,300 individuals. So there is a clear bottleneck that lasted for about 100,000 years. So we are all cousins, by the way, because our ancestors were so little that then we had a very, very few number. And then after this period of time, the population of hominids started to increase again until the sapiens and the spread from Africa to non-African evolution and so on and so forth. So basically, this is centered into this mid-Pleistocene transition. Is it that linked to that or not? Well, we have to look at that. It is something, the transition, something happened not because of the orbital parameters, because if you look to the obliquity or the precession and eccentricity, or basically the solar insolation over the last 2 million years, you don't see any different changes. There are many factors, physical ones. So as I told you, it becomes more and more difficult to deglaciate. If, let's say, the size of the ice sheet goes above a certain threshold, is more and more difficult, and it can be happen that, but it can be also something linked to what is called a non-ice sheet mechanism, which is called the regolith hypothesis. So the fact that you have very silty sediments underneath the northern hemisphere ice sheet that relaxing and growing, relaxing and growing. At a certain point, this very silty and slippery sediment went away, and so on a crystalline basement, the ice sheet started to grow much bigger during the most recent years. Well, again, this is a highly debated hypothesis. There are no many clues around that, and so most recently, looking at many different records, it is reported that there is a clear role in the Southern Ocean, and the fact that there was a dropping in the temperature in the Southern Ocean exactly centered in that. So there is still a lot of unknown. I mean, so hypotheses are around, and if you want to disentangle that, and if you want to know more about this iconic period, we need to have a record in which we have the temperature and where we have also the greenhouse gas. And so the only way we can do that is to look and to have another ice core, a continuous record of an ice core. So 10 years ago, we started a race for the Holy Grail. There are many nations seeking for the oldest ice in Antarctica. There are at least 7 consortia trying to find the oldest ice in Antarctica. The Japanese are drilling in Dom Fuji. They are all along the ice divide in East Antarctica. The Chinese are on Dom A. The Russian are in near Ridge B, near Vostok Station. And they're near Concordia, our Italian-French station. There is an European consortium that actually is led by Italy. There is an Australian consortium and a Korean one. And plus there are the Americans and also the Chinese working on what is called blue ice, so area in which the ice is coming up again, and so where we can find fossil ice, but it's not a continuous record. So we are seeking for very old ice where we have low accumulation, where is enough cold, especially cold at the bottom, because we don't want to have melting at the bottom, otherwise we will lose the resolution. And of course we look at a place where the ice is not moving that much, no? So not much lateral flow. So and this there that we went to have our project. The project is called Beyond Epica. Epica is the iconic project, is the European project for ice coring in Antarctica, the one that reconstructed the CO2, greenhouse gas, and temperature concentration over the last 800,000 years. And we want to go beyond that, so seeking for ice as old as 800,000 years. Well, we spent more than 3 years for a survey in the region. This is on the bottom here, is Concordia. We run more than 20,000 kilometers of radar line and survey, geophysical survey in many different regions. And then we concentrated on a southern patch here, on the region here, where we had a radar echo sounding at the 200 meters distance from one to the other one. So very, very high resolution. So we could reconstruct the bedrock topography at a very high detail. We could also connect the radar line from Concordia to the new camp, the new region. So looking at, and the Concordia ice core has been dated very well, so we could follow the radar line from one place to the other one, reporting all the lines, and looking that in these sites there are also reflections, so horizons, which are much older than what we had in Concordia. So we basically decided, let's go there. We don't have too much fantasy. We call the new place Little Dome Sea. It's just 35 kilometers away from Dome Sea. And this is the depth age scale, and you see it in blue. So the model tells us that we can find ice as old as 1.5 million years. So this is our hopes, and it is where we are drilling right now. And very recently, so in the last years, we also saw that even closer to Concordia Station, in a place which is called North Patch, which is about here at the bottom of the picture, there is another place which is probably even more promising, and is the orange curve down here, where you can find ice which is probably 2 million years size, or old ice. Well, you might argue why you don't go there, but it's because we started to drill 5 years ago, and the new data came available very recently, and actually the Australians are moving on this place. So we start drilling some time ago. We are still drilling. The depth that we reached last season is 1836 meters. We have definitely the oldest ice, more or less at about 2.5 kilometers, and the last 200 meters is what we call stagnant ice. It's not really where we see from the geophysics, we don't see any layering of that. So most likely we have to reach to obtain the oldest ice, the depth of about 2.5 kilometers, as is doable this year. We are deploying the team in the field in these days, and this is the drilling tent that you see here. We have organized the camp like that. The drilling tent is this one. Those are living modules. We have a cave dug into the snow. We have 6 containers buried into the ice, because we want to keep the ice at minus 50. This is allow us to preserve all the gas and all the information of the gas inside the ice matrix. Average temperature in the field here is about minus 52, and in summer we move from minus 30 to minus 60. Inside the cave we have a constant temperature of about minus 35, minus 40, while operating and cutting and preparing the ice. Well, we do also measure several parameters on site, especially we want to know where we are, so we measure stable isotope directly in the field. The black one is the EPICA, the Dome Sea record, the one that go down to 800,000 years. This is what has been done in the field, so we can monitor day by day where we are with the drilling, so we know exactly where we have to intensify and to be more careful in the drilling. And well, this is the age that we reach, we more or less reached last year. Of course, the deepest part of the core is squeezed, and so it's compressed, and we think to have about 20,000 years in about 1 meter of ice. So the oldest ice, the ice older than 700,000 years, will be most likely squeezed in 200 meters of ice. So we are pushing a lot. also for new analytical method, new tools for the analysis of the ice core. Well, I think is all I wanted to say. There are multiple reasons why we have to be interested in polar regions. So everything, all things that happen in the poles are have a strong influence in lower latitudes, with the differences in transport, changes in transport pattern of heat and material and water, and so that's more and more important. And then many other reasons as you have seen. Before to finish, I just want to make you an advertisement that ENGV is already participating to the Italian National PhD program in polar sciences. We have 6 different curricula on climate system, on biology, ecology and biodiversity, on human impact, solid earth, ocean and cryosphere, astronomy and earth observation. It's brand new. We are delivering every year about 30 grants, so spread the voice. And thank you very much for your attention.
Thank you, Professor. And so for those attending online, you can please fill up the form that it's in the same link they received for attending online. And for in-person attendees, if you could ask your questions, we can circulate the microphone.
Well, thank you, Carlo, for this very, very interesting talk. We knew, but you explained it very well, that ice coring is essentially very important for understanding the climate change in the history and so on. But you gave us just a very short description of the new work, where we have a lot of expectations with this beyond Epica. Can you tell us something more? You have a confirmation of fluctuations of CO2 and temperature at the same time. What do you think is something that we can understand more than what we had in the past?
Good point. I mean, I can't tell you because we don't have the samples. We might meet together in a year or 2 years from now when we will have the samples and analyze them. There is a lot of expectation, and many modelers already starting to try to predict the past. You know, to reconstruct the CO2 variation in the past due to the Beyond Epica experiment. This will be very important to see the relative changes in CO2 and the temperature. So we are really looking at that. We really don't know how they will look like. Depend on the role, because one of the most important things about the mid-Pleistocene transition is tightly linked to the role of the Southern Ocean and the role of the biological pump in the Southern Ocean, and this is tightly linked to the CO2 concentration that we will find. But again, this is why we are there. So otherwise we would have rely on models, and that's it.
Thank you. Thanks for your question, Tony. Meloni. For those online, we cannot probably see the faces. And now Fabio Florindo.
Thank you, Carlo, for this very interesting talk. I'm curious about 2 things about the ice drilling. From years, I have this. How do you control the CO2 diffusion? I know that in Epica you drilled more than 3,000 meters, and I imagine at the deepest of the coring, the CO2 can diffuse. How can you control this? And the second question is about the dating. How do you define the chronology of the ice coring? What is the methodology?
Good point. In the meantime, I run this little video so you can see the camp and the drilling tent and the operation. First things you ask about how we keep the diffusion of CO2. Well, something that we are doing now, respect to what we did in Epica, we are keeping the sample at -50. all the way around, all the way from the sample site to the laboratories, and that's a huge effort, you know, to transport sample at -50. There are no commercial freezer. We have to build a freezer. Of course, everything is duplicated. We have to be redundant in all the cold chain, and so this is the way in which we preserve the CO2, and not just CO2, but also other gases like argon, for instance, for the dating. Because again, for Concordia, for the Epica core, we mostly dated through tuning of the climatic signal with orbital signal. In this case, we do the same, but we dramatically improve the absolute dating using chlorine or using argon dating, argon-potassium dating, which is now doable also in ice cores. We need a lot of sample for us, and let's say 1 kilo, which is from an ice core is a lot, I tell you, but it's doable. And something we want to do also for improving our dating capability is also to have replicate core. So from a certain depth, we have another, we divert the ice core, and we drill a parallel core. So we have more sample for the dating and more sample that can be used for improving our dating with absolute methods.
Thank you. Now we have a question.
Marco Ansidei, NGV. So thank you for your very interesting talk. Just a comment on sea level rise, because the IPCC does not, in the expected scenario, does not include the land subsidence along the coast. So this is a mean sea level rise. So, but in some areas, the expected values can be double or triple the values shown by the IPCC. This implies that along in some regions, the expected impacts of sea level rise could be very strong, because, for example, we already know that in Indonesia, for example, or even Italy, in some areas, land subsidence is playing a fundamental role in the expected future scenarios of floodings.
Fully agree, and I'm perfectly aware about that. It's just a general view. Of course, I'm living in Venice. I mean, I'm pretty sensitive to that one. Thank you.
Okay, thank you. We have another question. Tommaso Alberti.
Thanks, Carlo, for the nice talk. Just a question about you mentioned that for the mid-Pleistocene transition, you mean different records from temperature and also greenhouse gases, no? The main problem is that what I see now in tipping points is that we do not control which is the effects of short-term processes on the large scale. So, for example, transition between different climate states can be differently depending on ages of the different things. So, which is your feeling in the next generation of ice cores in terms of improving the time resolution of the records?
Thank you. Good question. I tell you, I think I have it here. We are working a lot on that. Since I told you that all the styles will be squeezed in literally in a couple of 100 meters of ice, it means that we have a time resolution which will be about from 20 to 30,000 years per meter. So with the current techniques, we are losing information. So we are working a lot on improving our analytical capability. And what we are now using is we use laser ablation, the same that you use for marine sediments, for the analysis of ice core. So in that case, instead of having half of centimeter resolution or a centimeter resolution, we can go down to 100 micron resolution. So with a very, very high detail. And above and on top of that, you can also have information about distribution of impurities into the ice. This is a little tiny piece of ice of about 35 millimeter by 7 millimeters, but it gives you a chemical imaging of where all the species are. In this case, sodium, magnesium, and strontium. As you see, they goes on the boundary of the grain layers of the ice. Well, knowing and having those information and bringing and scanning all the ice with these techniques, we plan to improve dramatically the climatic signal, not just for trace elements, but we also applying this technique with stable isotope analyzer. So looking at the isotopic composition, scanning with the laser, so improving dramatically the resolution. And again, as you say, the devil is in the details, so that's the reason why we're working on that.
Okay, thank you. We have another question from Alessandro Amato.
Thank you for the talk. I'm not an expert in this field, so my question may be stupid, but I'm curious about what you mentioned about you call them low probability, high impact events like black swans or whatever it is. So which may be these events? You mentioned something about the collapse of the Antarctica, but there are other.
No, there are many sites around Antarctica where those events can happen. Twice Glacier is one of those, and is probably the most famous, the most studied, and the largest one in Antarctica. And is where we have an ice shelf, which is actually protecting the ice sheet inside, but is degrading very quickly. So if you take out this barrier, this ice sheet can increase the velocity. So, and it's something which is literally happening. It depends how fast this will happen, and it's still a big question mark. There are a lot of modeling exercise going on that. And there are other sites, other places around Antarctica and in Greenland as well, which is even probably more dramatic, but things are happening quickly. And we also don't understand the probability because we don't have analog in the past, so we don't see them very frequently.
Thank you. Other questions? Leonardo Sagnotti.
Grazie Carlo for this very interesting presentation. I have one remark and one question. One remark refers to the development of our species. As you showed, Homo sapiens went out of Africa essentially during the last glacial period. And then for several tens of kilo years, did not develop any cultural or scientific development. And if you can go back to the slide with the Danskar-Eshed oscillations, the last glacial period was a period in which, as you pointed out, there were very sharp and short events of temperature changes, marked there by numbers, which lasted from the beginning of this last glacial period up to the last glacial maximum, around 20 kilo years ago, with also one evidence in the deglaciation, the so-called Jagger-Dryas. The Holocene instead lacks these wide oscillations, and the Holocene is the period in which our societies developed. We developed farming, agriculture, arts, literature, and everything science, everything which characterize technological developments, everything which characterize our societies. So it seems that Homo sapiens, to improve and to develop ideas and technical solutions, needs a stable climate. So everything you showed is highly relevant to us. As you said, there are several reasons for putting the highest attention for science, but also for, let's say, for public or for policymakers to what happens to global climate and Arctic and Antarctic regions, polar regions. So there is almost, this is the question now, there is almost a total scientific consensus in what's happening now and how this could impact our lives and the future, or our sons, future generations. So there is almost a complete agreement in the scientific community. But all these facts and implications are very difficult to be spread among policymakers and general public, which it's difficult to see what they mean, to accept the implications. What could we do as scientists to improve this and to make the warning and the concept more available and easy to be digested and accepted for policymakers and the general public? According to your experience, you have a quite wide experience in these topics over several decades of scientific activities, and I imagine that you can feel that there is a difference when you talk to us as scientists and when you talk to the general public, which are not experts of the field.
Yeah, good question and very difficult. Although I must say it's not just from a scientific point of view we know everything. We also know that from a financial point of view we have tools for fighting the climate crisis. We have legislation from at least in Europe, a pretty good legislation on that. We have the economy we know quite well, and we have also the technological way in which we can afford all that. So, because in any sector from production of the energy, from chemicals, we know that we can tackle the situation. The point is how to make politicians thinking about that, and I think we need more events that puts together scientists and politics. That they are very, very scarce, and then I think Carlo can tell you. I mean, it's not easy to speak with them. Something that I saw is working very well in the Arctic, for instance, is a form that is called Arctic Circle, and we were in a few weeks ago actually with Giorgio Di Sara over there, and it's a place where you put scientists with politics together, you know, but real policy, politics, you know. There were prime minister, there were head of states, minister of resources, and they stay all together sitting in a room and discussing about science and about politics. So I think there's a format in which everybody touch with hands what's going on. Of course, there are priorities on life, you know, and I can't see Joe Biden or Putin sitting together discussing about climate today. And that's the other aspect that we have to consider. But I think that the format of bringing together science and politics in the same, discussing each other, you know. It never happened to me to ask a question to President Macron, for instance, and it happened to me last year, for instance, you know, and having a feedback and really, I think that might be the solution, but we need more than that.
Okay, thank you. Maybe a little advertising I could use. Also, EGU is really committed in the last year. They build up an entire EGU policy and they do events all the time. So maybe, Leonardo, if you're interested to join. There is always the need of any career stages and
but
any.
Then again, you advance and then you go back. I tell you a story. We were coming back from a mission in Ghiacciaio del Mandrone, you know, in the Adamello region, where the ice lost 17-meter thickness in a season, you know, and then we had a press release of what happened and so on and so forth. And the day after, there was a comment of a minister of our government, I don't tell the name, that says, wow, It's not because my colleagues goes back and forth to Passo dello Stelvio with this car that the Mandrone is disappearing, you know. This is the level that we have. So I think we have to work a lot. We have to work a lot.
Thank you.
It's a windy road.
Are there other questions? Online, I don't see any questions. If you wanna, yeah, I come. If you wanna ask questions online, you can fill the form that is there. It's a Google form, and I will read it out for you. Fabio, second question now.
Yes, second question. I don't know if we have time. Carlo, at what stage is the discussion about the bipolar connection in climate change? The connection between North and South Pole.
Is in at what stage it is right now?
Yeah.
There's plenty of discussion running, yeah, of course. The bipolar seesaw and the modeling of that is quite in an advanced stage, yeah. There are more and more data, more and more modeling exercise proving that there is a teleconnection in between the two hemispheres, which are...
Is there a consensus about who is driving the
Well,
other?
again, I'm not an expert in dynamics, but yes, is a mix of ocean and atmospheric forces that is driving that, and there is a delay time, and usually when we are cooling the north, the south is warming, so it's out of phase.
Okay, thank you. Any other question? Yes, Carlo Doglioni.
I may have lost the explanation why the effects are so most important in the northern pole with respect to the southern pole.
Again, is a problem of dynamic of climate and the circulation of ocean and air masses and atmospheric masses. Is proved by experiments and also by modeling exercises as a reproducible process. Is tightly linked to the ocean circulation and atmospheric circulation.
Thank you. Any other question? I don't see questions online either. I can ask one if that's okay.
Sure.
If you could please pull out the map of Antarctica with all the parties, Risico parties playing out. The US, the Italy, France, and...
Which one you mean?
The one where you have all the projects.
Ah, okay, I understand that one. Is here. It's coming.
I asked a difficult question. Okay, thank you. So I love correlation, so my question is going to be about cross-correlation between the data already obtained. So you have similar time frames, maybe 800,000 years, and how well do these data correlate between each other, say Vostok Epica or between far-reached cores? If you can see any different influence into the different climatic systems, or is that just one same system?
Good
Thank
point. Well, there is much more than that in Antarctica in terms of drilling activities, you know, it's pretty spread around. Usually the data correlate very well. They correlate well also with the northern hemisphere. And we use methane, which is a gas with a very short living period. So if you find a peak in methane today, the year after you find it in Antarctica. So it's very well correlated. So we use methane records to match the ice cores from the north to south, and therefore you can well correlate. And even in Antarctica, we can correlate it well. You see differences. We were discussing about dust, for instance, before. We see differences in dust concentration. We see differences because the dust is coming from different sources, and we can track back the sources looking at the isotopic composition of the dust, neodymium, strontium, rare earth elements. So we can look at that. But usually the climatic signal that we see in ice core is a global signal, which mostly represent the entire globe. But we need more records anyway.
Okay, thank you.
Most
We'll
likely.
keep drilling then.
Please?
We will keep drilling then.
Sure.
Any other question? No online questions.
Super.
So yeah, big round of applause again, and thank you again, Professor.
Thank you. And, happy birthday to Ian Givu.
Happy birthday.
Thanks for inviting me.
Super interessante, grazie mille.
Grazie a voi.